Yeah, I'm Andrew Jordan, and I've been at the University of New Hampshire now for almost 4 years, working on the Lunar Reconnaissance Orbiter. All right, so I'm just going to give an overview of the mission itself, in particular looking at kind of the background of how um, folks put together a spacecraft and then send it to the moon, because that's something that I wasn't directly involved in. I joined on afterwards as a scientist, but I really enjoy finding out what goes on, the technology behind these spacecraft. And then I'll talk a little bit about some of the general results from LRO and, in particular, some of my work to using data from it. So this is the beautiful picture of LRO. It really doesn't look like that. I'll show you what it really looks like. And you can see it's basically just a big box. It's a little bit taller than a human. It's maybe 10 feet, 4 meters tall. And right here are almost all of the instruments. And then there's a few more instruments here, and I'll work through all of those later. So what do you need to get a spacecraft to the moon? Well, you need an idea first, but you also need some money. And in the case of LRO, you need $500 million, which is rather cheap. Although I just heard that India got a spacecraft to Mars for 70 million, so maybe 583 million is not so cheap. You also need places to build the instruments on the spacecraft. So you can see these are instruments. I'll step through most of these at some point during the talk. A number of them were built in Arizona. Diviner was built at UCLA. The cameras were built in Arizona as well. This instrument called LAMP is built in Texas. And Crater, which is the one that I'm interested in, it's the Cosmic Ray Telescope for the Effects of Radiation. I'll talk quite a bit more about that. That was built in Boston, and now it's being run out of here at University of New Hampshire. And Lola was built in Maryland. And Maryland is where the spacecraft itself was assembled. And then the last instrument, Mini-RF, which is a radar instrument, that was also built in Maryland. And then the spacecraft launched out of Florida. So all the instruments were built in these different places, and they were shipped to Maryland, where they were integrated into the spacecraft. And then the spacecraft was driven down to Florida. So there you can see what it looks like. There's a big fuel tank in the middle here, and then they attach a box around the fuel tank. That's called the bus. And then this thing right here contains most of the instruments, at least about half of the instruments. And this is what it looked like when it was ready for space. All the instruments and the spacecraft have been wrapped in a thermal blanket to protect it from the extremes of heat and cold. And it doesn't look like much, but it gets the job done. And you can see the different instruments. So there's the Cosmic Ray Telescope for the Effects of Radiation, the Crater. There's Diviner, and I won't go through all these instruments because I talk about them later on in the talk. It's really not much to look at. So this is taking place down in Goddard. All the instruments have been built and tested. Now they've been integrated into the spacecraft. And now that the spacecraft's been put together, it needed to be tested. And this was back in 2009. A lot of these tests were run. So this is at the NASA Goddard Space Flight Center, just outside of Washington, D.C. This is the acoustic test chamber, and just for scale, there's a door right there. This big horn-like thing, that's maybe 4 or 5 feet tall. This is a subwoofer, and these are tweeters. So these are massive speakers, and what they do is they put the spacecraft in this room, and then they blast it with sound waves. And the sound from this is the equivalent of standing next to a jet fighter before it's taking off. You can see over here the bay doors. Those doors are about 1 meter thick, and they're solid steel and concrete filled, I think. So they put the spacecraft in this and then blast it with sound waves to simulate what would happen during launch with all the aerodynamic turbulence going on. And apparently it's really loud. When they do the full-blown test, they actually evacuate everyone out of the building. And the building is pretty big, but apparently it's so loud you don't want to be anywhere near it. LRO survived, thankfully. That's always a good thing. And was put into the Space Environment Simulator. And here you can see a man sitting down next to it. This is the size of a small house. And what it does is they take the spacecraft, they plop it in, and then, well, they don't plop it in, they lower it very gently. And inside is a vacuum chamber. It's a really big vacuum chamber, but the nice thing about it is that it can alternately bake LRO, so it can bring it up to really extreme hot temperatures, but then also bring it down to really cold temperatures. Because when LRO is in sunlight, it's going to get really warm, up to about, I know this is in Fahrenheit, I don't know it in Celsius. It's about 300 degrees Fahrenheit, and then minus 300 degrees when it's cold, when it's in the shadow of the moon. And so it was in there for about 2 months, I believe, at the end of the year 2008. And again, it survived. And the reason they do this is because electronics work very differently when they're in vacuum. Like all the computers that we use here in the atmosphere have fans to cool them down, but you can't do that in space. So this just makes sure that everything works well as a whole. What you're looking at right here, that's the antenna that LRO uses to talk to Earth. So LRO survived that. You do need a truck to get to the moon. Trucks are very important for getting to the moon. So LRO is packaged up in this box, and then they drove it down from Maryland all the way down to Florida. And they drove it overnight. It was a pretty long trip. And they drive it at night so they can avoid all the traffic jams, because you don't want LRO tipping on its side and ruining $500 million worth of equipment. The rockets were built, well, these are Russian rockets. This is the Atlas V. There's Russian rockets. This is actually, I believe, a Russian aircraft that delivered the rocket. There's an upper stage rocket that is assembled and tested out in the western United States. So it's a pretty big rocket. Now it's being driven out by another truck, so you need multiple trucks to get to the moon, out to the vertical integration facility. And a crane pulls the rocket up into place. And then also in Florida, LRO is attached to its twin spacecraft LCROSS, which is an acronym that I've never been able to remember. LCROSS is basically, it was a spacecraft designed to crash into the moon. So it was a suicidal mission, but it's supposed to kick up some ice near the poles of the moon, and it actually did. It was a successful mission, but I won't talk much about that. We'll just talk about LRO. And LRO is wrapped inside this cone-shaped fairing, and that keeps the rocket aerodynamically stable. So LRO's inside that fairing up there. There's another rocket that I didn't show you. That's the second stage. And then there's the Atlas V rocket on top. So they've all been integrated. And the whole thing is about 200 feet tall. Inside this building, and you can actually see this big, tall tower right here. That is that right there. So the whole rocket, well, it's assembled in this building, actually can roll out on these railroad tracks, and they can drag it all the way out to its landing site. So it's just like the space shuttle was dragged out. And here's a nice shot of it going all the way out. And then way in the back, you can see the space shuttle. I think this was Endeavour on the launch pad. There was a bit of a traffic jam down in Florida about whether LRO was going to launch first or the shuttle would launch first. And the shuttle kept LRO on the ground for a little bit, but they had a leak, so eventually LRO launched. And then there's LRO sitting at the launch pad. You might notice these 4 towers right here. Those are lightning rods. So you also need lightning rods to get to the moon, which is not something that's usually on my list of things to use. And that's why the afternoons in Florida often have thunderstorms. This was just the day before we launched, I believe. It was a pretty exciting thunderstorm. One of my friends took this picture. This is back to the moon party. We're all excited we're going back to the moon, and here's this horrible storm rolling in. But it didn't matter. LRO launched successfully with a couple minutes to spare. We had very tight launch windows, certain times that we could launch. And the weather wasn't really cooperating because you can see how cloudy it was. But it was just good enough that we were able to launch on June 18th, 2009. So after launch, we got to the moon in about 5 days, or LRO did. I didn't get there. But in order to make sure that all the data get to Earth, LRO transmits data to a satellite dish down in New Mexico. And that's always in contact with LRO. As long as LRO is above the horizon, we can get data from the satellite dish. We can also use other satellite dishes around the world, but we tend not to. Then those data are sent back to Maryland, where LRO, the spacecraft, was assembled. The data come from LRO to New Mexico, then they're sent to Goddard again to the Mission Operations Center. I'll show you a picture of what that looks like. There's a number of spacecraft that have their Mission Operations Center in this building. This is LRO decked out for Christmas. You can see the ribbon. And there's a map of LRO where it is above the surface of the moon. And then these are the commands that the men can upload or receive from the spacecraft. So they keep track of it 24/7. There's also a backup Mission Operations Center somewhere in Pennsylvania, just in case this one gets destroyed or something. They do have a backup. And then from the Mission Operations Center, or the MOC, it's called, all the data are split up and sent out to the SOCs, or the Science Operations Center. And one of those is the building that I'm in, Morse Hall, on University of New Hampshire's campus. This is actually a very nice picture of us. My office is exactly opposite where my cursor is, way on the other side of the building. And so then we have computers here that translate the data into things that we can actually use for research. And then some of the data we send back to NASA to store on their servers as well, and we keep copies. So that's how you get to the moon. I'm tuckered out. Now, just to give a little bit of a summary of some of the more recent results from the spacecraft. So this barrel, you can't really see it behind there, but there's this, and there's a twin one behind, and then this little piece here, I'll show you a real picture on the next slide, is the Lunar Reconnaissance Orbiter camera, or LROC. So it's these two barrels are these are narrow angle cameras, so they take these really zoomed in, high detailed pictures. And then on top, I don't have it labeled, but that's the wide angle camera. So it takes a really, has a wide angle lens, so it takes a picture of a big swath of the moon. And you can see how tiny it is. It's about the size of a pocket knife. So they can get the context of the pictures, and then they can get details within the context. So this image right here is a mosaic of, I think, about 30,000 images from the wide angle camera. You can actually see the little stripes where they haven't been stitched together all that well. The images are getting better and better as they get more data. But you can see, and you can zoom in on this. If you go to LROC's website, they do have a map. It works like Google Maps. You can zoom in until you can see things that are only a fraction of a meter across. It's pretty amazing. And this is one of my favorite locations on the moon up here in the, I think it's the Apennines. And some of you might recognize this. This is Hadley's Rill. So a rill is probably a lava tube that's collapsed when the lava solidified. It's about as big as, well, it's about a couple kilometers across and a couple kilometers deep. And that picture right there, or that area right there, was actually visited by the Apollo 15 astronauts. So this is the first mission where Apollo used a lunar rover back in the early 70s. And so this is the view looking back down the rill. So they're looking in this direction along the rill right here. They're just on the edge of this mountain right there. It's pretty amazing. People were walking around down there a long time ago. And if we look at this area, this picture is from LROC as well, and you can actually see this little dot. That's the lunar module. That's the lunar rover. And then this is where they actually drove out and visited some of these areas. Yeah, you can hardly see it. I'll blow it up for you. If we zoom in on that, that's what it looks like. There's the lunar module. There's the lunar rover. And all these dark tracks that you see are footprints that are still there 40-ish years later. And these tracks right here, the lighter ones, these are the rover tracks. So they're still pristine. They're going to be there for probably another 1,000,000 years or so. So check back in 1,000,000 years and see if they're still there. And then LROC does do science. It doesn't just take pretty pictures like that. One thing that they've been focusing on recently, the team, has been looking for recent craters, so craters that have formed within LRO's lifetime, so within the past 4 or 5 years. And this crater was formed a few years ago, and LROC had been lucky enough to capture a picture before it formed, and then you can see what happens after. So now we have a great laboratory. We can actually see what happens when an object strikes the moon. How does the ejectiform, so the material that's blown out of the crater, how does that affect the surface? What happens with the coloration? How does it reflect the light? So that's pretty amazing. They've got a number of these before and after pictures. And then this one I have to show just because it's so pretty. On the far side of the moon, you can see it's much more heavily cratered than the near side of the moon. But there's this big impact crater here called Topographic, which I believe is named after the father of rocketry. He was a Russian back in the late 1800s. And after the impact, lava filled the floor of this crater, and that's why it's so smooth and dark. This is a picture looking at this central mountain in the middle. It's just kind of eerie, these white cliffs rising up out of the dark lava plains. I'm not a geologist, can't really explain any of the science in these things. Another instrument is LOLA. It's right here. This is what its innards look like. So it has a laser transmitter. That's that little opening right there. The laser comes out of that and is received by this. So it uses the laser to measure the distance from the spacecraft to the surface of the moon. And from that, the LOLA scientists have been able to build the highest resolution topographic map of the moon that we have, so measuring its altitude to within a meter or so. Now it's actually, I should have pointed this out earlier, before LRO, we had better maps of Mars than we did of the moon, because NASA keeps sending spacecraft to Mars, but now we finally have better maps of the moon than of Mars, just within the past few years. So on the left, you can see the topography maps. So it runs from -5 kilometers down in the lowest regions, all the way up to over 5 kilometers in some of the highest regions. There's some pretty tall mountains on the moon. This dark region down here, it's really deep. That's the South Pole Aitken Basin. It's the largest impact structure that we know of in the solar system. So something big happened there a long time ago. Something really big hit the moon. Based on how the laser light comes back to the spacecraft, they can actually measure slopes, which is really useful for planning future astronaut traverses across the surface. And it also, you can see, really highlights the craters in a different way that the topographic map doesn't. So they can get that from the data. And then this is really interesting. They can get roughness. So how many boulders there are in the region. And are they big boulders? Are they small boulders? They can figure some of that out from this. And this helps scientists figure out what are newer features. They tend to be a little rougher. So all of these maps are looking at exactly the same area on the moon. You can see how very different they are. Again, I'm not a geologist, so that's about all I can say about this.